Hi everyone, welcome back to our Calculus 3 class notes. We are in the middle of page 34. We're starting section 13.4 where we're going to learn about curvature and normal vectors of a curve. So definition. So we just learned about the unit tangent vector. If t is the unit tangent vector of a smooth curve, then the curvature function of the curve is this kappa, right? So kappa is the magnitude of the rate of change of the unit tangent function with respect to arc length. So you can imagine this unit tangent function at any point. And so what happens is the unit tangent function doesn't change a lot in direction if the curve isn't curving, right? So now if the curve starts to curve more, you can see how the unit tangent vector changes a lot with respect to the arc length, the curve. So if I go along the arc length a certain distance, the unit tangent vector is going to change a lot where I have more curve. So this is how we define the curvature function. It's an extremely useful number to compute as it tells us how sharply a curve is turning. If the magnitude dt ds is large, then the unit tangent turns sharply as the particle passes through a point P, and the curvature at that point P is large. If the magnitude dt ds is close to 0, then the unit tangent turns more slowly and the curvature at P is smaller. This helps us understand curvature, but actually computing dt ds is not the way to go. It's a very hard thing to do. So we need some more calculus to find a better way to compute it. So just some basic calculus here. If I'm looking at the magnitude of dt ds, which again remember is curvature, then I can think of that as dt dt. So if we have the unit tangent vector, that's not too hard to do, divided by ds dt. But we know what ds dt is. That's speed. So 1 over this ds dt, right? That's an easy thing for us to compute. That's the magnitude of velocity. And dt dt is an easy thing for us to compute. So this is one way, a good way to compute curvature. There will actually be another way later that's even easier, but this is one way that's not too bad to do right now. So looking at example 32, let's find the curvature for the helix. R of t equals a cosine ti plus a sine tj plus btk. A and b are both positive or 0, so these are not negative constants. They're both positive or 0, and a squared plus b squared can't be 0 because you'll see when we finish it, we'll have that in the denominator. So let's find the curvature for this. So velocity is r prime. So r prime is minus a sine t in the I direction plus a cosine t in the j direction plus b in the k direction when I take the derivative of these guys individually. If I take the magnitude of v, the velocity, which is speed, so that's not too hard to compute. I get a squared sine squared t plus a squared cosine squared t plus b squared. Again, we can factor out a sine squared t plus cosine squared t. Factor out the a squared from these two terms, and you're left with a squared times sine squared t plus cosine squared t, which is 1. So you get the square root of a squared plus b squared as the magnitude of velocity. Now the unit tangent is v divided by its magnitude. So that's minus a sine t divided by the magnitude, which is the square root of a squared plus b squared, etc. for each term. You just divide each term by the magnitude. And curvature is 1 over the magnitude of velocity times the derivative of this guy, right? And when I say the derivative of this guy, I mean the magnitude of the derivative of this guy. So curvature is 1 over magnitude of velocity, speed, square root of a squared plus b squared, and then take the derivative of each piece here. So the derivative of minus a sine t is minus a cosine t. This square root of a squared plus b squared is just a constant because a and b are both constants, so that just stays in the denominator. The derivative of a cosine t is minus a sine t. The derivative of b squared is 0. Okay, so you end up with this. And after simplification, if we put this into one fraction, we can see that we can factor out a squared times cosine squared plus sine squared. I can bring out a square root of a squared plus b squared outside, and that's a square root of a squared plus b squared times another square root of a squared plus b squared. So I get 1 over a squared plus b squared. This simplifies to a squared times 1 under the square root. So I just get a, because a has to be positive or 0. So it's just a over a squared plus b squared is the curvature. So curvature is constant along this helix, which makes sense because curvature just is the rate of change of that unit tangent with respect to arc length. So as you go along that helix, the curvature is the same everywhere.